the right screen. So thanks, Ipek, a lot for this really nice introduction, and all the nanoTalks team for having me. And also welcome from my side to my talk on medical magnesium implants. I'm very much looking forward to take you on a journey through my world of materials. So let me start with implants that can be found for the human body. So the first implant that has been known that was implanted on a living human is actually a tooth. So as you can see, and I hope you see the pointer, this tooth here is actually a part of a shell valve that was implanted in a living human being. And we know that this person was still alive because the bone was actually attaching to this shell and holding it in place. Now, nowadays, these implants look much more sophisticated, and we have titanium screws that grow into the bone and covered with ceramic crowns. Now, what you might be much more familiar with are these titanium osteo implants. These are plates that are put over a broken bone and are screwed onto the bone to hold the bone in place while it's recovering. But there are also much more sophisticated implants, such as a hip bone implant, which consists of a socket in the femur stem and a ball in a ceramic or in a polymeric cup. And if we saw all the research that is done on hearts, also here synthetic materials are important, as for example pacemakers, which contain also electronics. But as we saw in the initial example, we have these natural materials, and even now natural materials are still really important for implants, such as these allografts by Straumann. So these are bone parts from dead people that are recycled basically to fit into other people. And we know that natural materials can be really good if they are treated well. But today, what I want to focus on are these bone implants, so such as this plate, for example. Now, you might be familiar with the current state of the art, which are usually stainless steel, titanium, or chromium cobalt alloys. Now, stainless steel is usually used because it has been known for a really long time and the body accepts it really well. Titanium, as we will see a bit later on, it's a bit more closer to our own bones' mechanical properties, and this is really important, as I will show you later. And cobalt chromium alloys are usually used in knee joints, for example, because it's similarly strong to stainless steel, but even harder, which is important in heavily loaded joints as your knees. Now, for now, I want you to remember that these materials are really good materials. They are well proven. However, we always look for the better, right? So I want you to introduce to the small drawbacks that these traditional materials have. So one is the thing called stress shielding. So as I explained to you before, stainless steel is actually a lot stronger than our own bones. So if we compare the stress distribution on a loaded bone without an implant in, we see in these red zones that the bone is heavily loaded, whereas the blue zones are a lot less loaded. Now, this changes if we introduce an implant, such as this total hip replacement, into the bone. Now you see that the red zones are actually scattered a lot more, and they are in zones where it has been blue before. So you have local stress concentrations in your bones, whereas other zones which have been red in the healthy bone are now suddenly blue, so which are loaded a lot less. Now, this is called stress shielding, meaning that the bone experiences less loading in places where it's usually loaded. And bone growth grows wherever it is loaded. So with these implants, we have a changed stress distribution and hence bone remodeling, which is in this favor for our bones. Now, another bad thing about these traditional materials is that they are meant to be bioinert. So that means that they are meant to stay there forever and not interact with our body whatsoever. However, these materials are actually not. So we still experience some corrosion, for example, steel or titanium implants. And what you see on this chart is that corrosive attacks are actually one of the most often reasons for implant failure. So it's up to more than 20% of the implant failure is actually because of corrosion attacks. Now, this releases ions into our body, and sometimes in the case for chromium cobalt, for example, these are even toxic for our body. But it's not only the ions, also particles are released. So as you see on this picture, these are red cells, and these black dots here are titanium particles that accumulate in the blood. And last but not least, we have the problem of implant removal. So as you saw, there are some problems with these implants. So whenever these implants are not used anymore, we want to take them out of the body. So you might notice from yourself, if you have a broken bone, you need an implant, and some years later, the surgeons want to take these implants out again. This is especially critical for children because they're still growing. So we want to take the implants out that the bones are allowed to grow again. Now, this means a second surgery, which is involving additional costs for the surgery itself, but also for the work absences of these patients. It's the risk of the surgery. Every surgery has some risk to it. And finally, it's also another pain for the patient, which is specifically hard to explain to children. So we are looking for a material which basically just disappears once its job is done. So as I mentioned in the beginning, mechanical properties are really important. So let's have a look at the mechanical properties of different metals. So what you see on this chart here is that the strength of the material versus the Young's modulus, which is a measure for the elastic property of a material. And what you can see here are the traditional materials in blue that I explained to you before. So chromium and steel, which are actually really strong and hard, and titanium, which is a bit closer to cortical bone here in this bone color. And what is really close to cortical bone is actually magnesium. So let me explain to you why magnesium is a really good choice. So if I talk about magnesium, some of you might have this image in your mind from the sports classes to have a strong grip. But this is actually magnesium carbonate. It's not magnesium, the metal. Also really nice, but not what I will be talking about. Now, some others of you might have this image in your head, which are pills. This is actually magnesium citrate. But what I will be talking about is magnesium metal. So really the pure element magnesium. Now, even though magnesium carbonate and magnesium citrate are not the things I will be talking about, they're still important because they show how important magnesium actually is for our body and how well it is tolerated. So magnesium is a micronutrient. We need to take about 300 to 400 milligrams per day. And it's really essential for our immune system, skeletal health, cardiac and mental health also. So this is good to know, because if you remember all the corrosion artifacts that we had for cobalt chromium, for example, with magnesium, it will not be a problem. So let's look a bit deeper into the corrosion properties of magnesium. Now, for an implant to degrade and to disappear once it has done its job, we need some specific properties. And what we want is that the strength or the stiffness of this implant decreases at the similar rate as the bone healing emergence. So if we think about the degradation going too fast, the bone will not be able to support itself before the implant is gone. And the other way around, if the bone is already healed and the implant stays too long, this will be towards the bioinert materials, which we also don't want. So let's have a look how this process works with magnesium. So this looks really complicated, and I don't want you to understand all these electrochemical processes going on the surface of magnesium. What is important is this degradation mechanism. So magnesium, once it degrades, it forms water, and it reacts together with water and forms magnesium hydroxide and hydrogen gas. Now, this is the most important equation. I don't see my pointer anymore. Sorry. What is also really important is that down the road, in physiological conditions, calcium phosphate is actually formed. And calcium phosphate attracts osteoblasts, which are bone cells. So the overall process of magnesium degradation will help us to form bone on the surface. This is why magnesium is also called osteoinductive. Now, the other thing is, what is important is the formation of hydrogen. Now, you might be wondering, what hydrogen? Like, I don't want to have this in my body. And it actually is a challenge with magnesium. So what you see here are micro CT images of a degrading magnesium pin in a bone. And all these black areas around the pin, this is actually hydrogen gas that is formed during the degradation of a bone. Now, as long as this degradation is controlled and slow, the body can handle this hydrogen gas and it will dissolve and be transported away from the degradation area. Now, what you also see is that the bone is actually growing in the areas around the pin. And this is, as I said before, because magnesium enhances bone growth. So before I continue, let me go a bit through the history of magnesium. Now, magnesium was discovered in 1808 by Sir Davy. And only a bit later, elemental magnesium was first produced. In already 70 years later, first magnesium wires were used as sutures for bleeding vessels, but the real breakthrough in magnesium as an implant was done by Erwin Peyer. Now, he had a really funny story. So he had a boy that he treated that was 17 years old. And this boy had a broken leg, and Mr. Peyer, he implanted him a magnesium plate and screwed it on with iron screws. Now, only a couple of days later, he had to remove this plate because the boy was experiencing heavy pain because the magnesium was degrading so quickly. So Peyer was actually excited by this event, and he was challenged by the science behind it and was doing further research and experiments. However, a lot of scientists at the time were going towards these bioinert implants, so stainless steel and titanium, and not a lot of actually implantation was done in the 20th century. But if you look nowadays, there are actually several products on the market, so magnesium screws and also stents for the heart, as we saw before, which are made from magnesium. So what happened in the meantime that we are now able to control this degradation? Now let's look a bit more deeply into the corrosion of magnesium. So there are two main factors that can be done to control the magnesium degradation. One is the alloy composition. So what you see in this chart is the mean hydrogen evolution, which is a measure for the degradation speed versus the time of immersion of a sample into a simulated body fluid. The orange triangles display magnesium of conventional purities, whereas blue and green are higher purities magnesiums. And what you see is that we have a lot faster degradation for conventional purity, which contains some ppm of iron ions. Now, it was found that even like really low concentrations of impurities will make the degradation of these magnesium parts go a lot faster. And if we have really high purity of iron, we can control the rate to a really low level, which is actually even too slow, and some alloys will have to be added to increase, again, the degradation speed. So this was not known at the time of Peyer, and now you also know why this implant of this poor boy was degrading so quickly, because this Peyer was actually screwing it on with iron screws, and this was doing a galvanic coupling, and the magnesium was corroding like crazy fast. Now, the other thing that we can do is coating the magnesium with hydroxyapatite. Now, hydroxyapatite is the main part of our bone, about 65% of it. And we just grow it on top of the magnesium, and by doing so, we can decrease the hydrogen evolution by a factor of 10. Now, happy end. So we have our bone implants, we can control the corrosion rate, all is perfect. No, because if that was the case, I wouldn't have any research to do. So if we look at bone, we see that it's actually porous. It has this really funny structure. And also medicine is moving more and more towards personalization, as you see here on this skull implant. And so we need to find a way to make this porous magnesium. Now, there are two methods nowadays that are used to do this. One is a process called salt leaching, which is based on the compression of salt particles in a container. And then these pressed particles are infiltrated with magnesium melt. And as soon as the magnesium melt is cooled down and solidified, we just rinse out the salt in simple tap water. And this makes then our porous magnesium. So if we look at the real samples, that's how they look like. So we have these really nice uniform pores. However, we cannot really control the shape and the size of them. And also, as you see, they're connected through tiny little spots. So for thick parts, it's really hard to get out all the salt from the implant. Now, the second approach is 3D printing, which is super nice to do personalized medicine. However, magnesium is a little bit of a diva. So it's really in love with oxygen. So as soon as you have like one atom of oxygen around, it will react with it and form magnesium oxide. And magnesium oxide is really stable. So it will not be melted by the laser. Oh, I didn't explain to you how SLM actually works. So we have a powder bed of magnesium powder, and the laser is actually melting layer by layer and building up the object in that way. So if we look at the real parts by SLM, they look super fancy. We can control the shape and everything. However, if you look at the microstructure, what you find here in white are magnesium oxide shells. So they are not broken up by the process. So the part is actually a composite material. And this has really severe consequences for the mechanical properties, but also the degradation properties. So what we are doing in the lab now is combining the best of these two approaches. So let me quickly guide you through the process we develop. We 3D print a salt-loaded ink, so by direct ink writing, which is an extrusion process where we push out an ink through a nozzle and deposit it layer by layer. Then this 3D printed part is sintered to have pure salt scaffold. It is then infiltrated with magnesium, and then the salt can be washed out to get the scaffold. So this is how the real samples look like. We are able to reach porosities between 40 and 90% approximately, and the resolution is about 500 microns. This is how the real samples look in the end. So as you see on the top, this is the sodium chloride template. So we have these really round struts. We can stack them, we can put them laterally, however we want them. And they are tuned to about 500 microns because this is the size that osteoblasts, so bone cells, really like. And on the bottom, you see the transfer to the magnesium scaffolds with the circular holes as well. Now, for the macroscopic shape, so for the personalization, we have two means. One is by the 3D printing process itself. We can tune the shape, but also by subtractive methods. So as you see on the side here, this is an infiltrate. So the salt is still inside. We can drill it, we can grind it, and so on. And in the end, we can wash out the salt to get these really nice structures, whatever we like. So for the end, I would really like to thank my team. This is Martina Ciovo and Kunal mainly, and also my professor, Andre Studart, for the support. Also for this financial support of the group of ETH Foundation, SNF, and so on. And with this, I would like to thank you specifically for joining this nano talk and for following my talk. And thank you for your attention.